Hi, my name is Kathrin, a PhD student and associated member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about the work in the cluster, their research and the future of quantum. In today's episode, I'm talking to Dagmar Bruss, professor for Theoretical Physics at the University of Düsseldorf and a member of ML4Q. We'll be talking about Dagmar's career steps, the supercosmos project in astronomical technology, how a coffee break in Oxford changed her research focus to quantum key distribution, and her thoughts on the impostor phenomenon, and how it affects many young researchers. Hi, Dagmar.
Hi, Kathrin. It's such a long time that we haven't met each other in the morning in the corridor at 8:20, just before the lecture, and you were always so awake.
Yeah, and I'm also missing all the live tutoring and exercises, and however, I'm still having the early morning lectures, so it's...
Very good, but we don't meet each other anymore.
No.
But here we meet. That's great.
Yeah, I have some questions to you, to your research, to your way to quantum information, and also later a short game to play.
I'm curious.
Yeah, how was your journey to quantum information? According to your CV, you were also in astronomical technology, which is quite far away from quantum computing.
Yeah, that's true. Actually, my journey to quantum information was completely unpredictable. So, actually, I think I bumped into it more or less by coincidence. So, I did a PhD in Heidelberg on particle physics, which was actually even after astronomical technology that you just mentioned. So, I was working on symmetry violations, on discrete symmetry, so on parity violation. And and then I went to Oxford afterwards. Actually, it was like I wanted to leave academia after my PhD. I didn't see a future in particle physics, or at least I didn't see my future in particle physics, and I applied for a job outside university, but I didn't get a job. At that time, there was, even for physicists, high unemployment. I applied for jobs. I wrote not many applications, maybe 5 to 10 or so. I got one invitation, but they didn't take me. They invited 12 people, but there were 2,000 applicants for one job. And then I decided I go somewhere else, and I had an offer to go to Oxford as a postdoc, working on PT violation, so on violation of symmetries, of parity, and time reversal. And then I was there for 1 year, with a contract for 1 year, and I ran out of money. After half a year, 3/4 of a year, I was thinking what to do next. And my office happened to be next to the office of Arthur Eckert, who's one of the founders of quantum information. And my boss was actually on a sabbatical, so I was alone. And then in Oxford, you have these coffee and tea hours, you meet people and you chat. And at one point, Arthur said, well, I have this project. Would you be interested in working with Alice and Bob on these crypto things, etc.? And actually, it was more because I didn't know anything else, but I had talked to the people in this group, and I liked the topic very much. And then I joined this group for another year of postdoc in Oxford. And this is how everything started. So, and at that time, it was a very small field. So there were very few people in the field. I knew almost everybody in the world who was doing quantum information processing, and I was very lucky. So something that looked like being unlucky, not finding a job and emigrate to the United Kingdom because I couldn't find a job in Germany, in the end turned out to be something very positive. So, and then I had a good project at the beginning. I was involved in work on no cloning. So maybe you've heard about the no cloning?
Yeah, I heard a bit about the no cloning theorem, that actually, so that if I understood correctly, the qubit cannot be cloned in such a way, or?
Exactly. So if you have an unknown qubit, so if you don't know the state of your quantum information processing unit, then you cannot take a perfect copy. And this is because of the laws of quantum mechanics, linearity, unitarity, and this has been known not that long actually, since the beginning of the 80s. And so people knew that it's impossible to clone perfectly. And then the question that Arthur asked me, well, but if you cannot do it perfectly, how well can you do it? So you have to introduce a figure of merit and then you do some calculations. And that was my first project. And in the end, so if you say that the perfect copy would be fidelity 1, then I did this calculation actually for some months, it took me. And in the end, the answer was 5/6, which is, yeah, and I was fascinated by this topic. And then I just stayed because I liked to work there. And I didn't care anymore about future prospect, about whether I find a job or not. I just enjoyed doing the research at that time.
Yeah, I can totally relate to that because it's also a thing for me. I really enjoy research and not only I had once a part-time job with software development, and I missed the math, to be honest. So I can totally relate to to that point. And later you went to Torino, to Professor Rassetti.
Exactly, yes. I went to the so-called ISI, Institute for Scientific Interchange, which was a small institute in the mountains, and it was specialized somehow on quantum information. There were not many people in the group. Actually, there was another postdoc and me. But the Torino conferences were there. There was a famous series of quantum information conferences set in Torino in exactly this Villa Gualino in the mountains there. Well, in Collina, in the hills, I would say. And I heard actually, I think it was maybe even the first talk of Love Grover, who talked about the search algorithm that became very famous. And I also heard a talk by, this was probably not his first talk, but one of the first by Peter Shor. And I'm sure that you have heard about this famous factoring algorithm. So he found out how to use quantum mechanics to find a better algorithm for finding the prime factors of a large number. Actually, exponentially faster is this algorithm. And yeah, so I was there somehow in the first years of the development of quantum information processing, and it was a fantastic time, full of energy, full of, I don't know, this kind of adventurous feeling that we started a journey into some unexplored area. And I was really lucky to be there at that time, at the right place. So yeah, I was very lucky in the end.
Yeah, it's quite impressive meeting the heads of basically quantum algorithms and
exactly.
And so this is also the reason why you decided to become a theorist, or was there some point where you really thought, okay, I don't want to make experiments, I want to study the mathematical basics of physics?
Yeah, maybe that happened even before. So I did a diploma in theoretical particle physics also. And then somehow I wanted to do something else. And actually that's when I went to Edinburgh to do this Master of Science in astronomical technology. And I wanted to experience whether I'm better in theory or better in experiments. So that was an experimental master. And my job was to design an optical apparatus for scanning big so-called Schmidt plates, which are not even used anymore today. So these were big photographic plates on which there were pictures of the stars. And this was an apparatus that scanned this plate and was reading it out. And I think it was called supercosmos. So I was developing this apparatus which was called supercosmos, which was great. And it still worked for a long time after I left, but nowadays, of course, it's outdated. But what really drove me crazy then was that I didn't really understand what I was doing. I was playing around with these different parts of the system. And then at some point, our light source broke or was not strong enough, I don't remember, and we had to wait for almost a month to get a new light source. I couldn't do anything during that time. But in the end, this feeling that I don't really fully understand what I'm doing and why it works, this just drove me crazy. And then I decided I'm not an experimentalist. And I really want to understand in more depth why things work and how they work. And I decided to return to Germany, and that's when I moved back to theoretical physics and did a PhD in theoretical physics. And ever since, I haven't done any other attempt to do experimental physics. Maybe I was just not good enough for that, but I think my interest is more in the theory.
And how was your working day actually? So it's when I usually explain how I'm working, it's sitting at the desk or calculating in front of a blackboard, and people usually think, okay, and what do you beside that?
Yeah, that's true. It's not easy to explain people what actually makes your working day, what you're doing the whole day. Maybe nowadays for me it's easier because my life my usual working day has changed a lot since I was a postdoc and I was talking about Oxford or later in Hanover. At that time I was doing mainly science, and nowadays I'm really sorry about that, but I think it happens to everybody getting older that I don't do mainly science anymore. So the good days are when I have time to do science and the days which are not perfect but maybe a little bit less good are when I have to do many other things. So of course I'm teaching, I enjoy teaching, and now during the term quite a lot of time is taken by teaching itself and by preparing to teach, by organizing to teach, by thinking about exam questions, by preparing for seminars, reading the papers that are presented in the journal club, for instance, in our seminar. And apart from teaching and research, the third thing that I have to do is, of course, administration at the university. And this means a lot of things. So I have to, maybe my most important job is to acquire funding for the group. So to run the group, you have to find money to pay PhD students and postdocs. And this actually takes quite a bit of energy. The situation for funding is not bad at the moment. I mean, everybody's interested in quantum technology. There are a lot of projects. So I don't complain at all about this. So I think it's a great time to do quantum science. The things that I also have to do is like working in search committees for new professorships, or also announcing positions for my own group, choosing people. So I'm listening to talks by people who apply for jobs in my group. And actually now thinking about it, I think most of the things that I nowadays do in my working day, I haven't learned to do properly. I mean, when you study, you learn to solve certain questions, you learn methods in theoretical physics, you learn to solve exam questions, but you neither learn to teach, you don't learn to run the financial office of your little family enterprise, you don't get any training in choosing personnel. So the only thing that you learn when you study is you learn to learn. And later, when I started this position here in Düsseldorf, I had to learn a lot by just doing, by jumping into the cold water and by doing it. And I still learn every day.
But one can see the effort. It's you have a nice group, and
oh, thank you. I think so too.
And I mean, before the whole pandemic, we had also some journeys together.
Exactly, we had these nice group excursions, going for a hike in the summer, having a nice kind of Christmas party in the winter. But I hope really that we will come back to that as soon as possible. Maybe already this December. Let's see.
Yeah, speaking about efforts, are there sometimes struggles that you think you as you said, that you cannot take all the time for science, or you sometimes think you didn't accomplish everything?
I think there are many struggles, and you have to get used to the fact that you don't manage to do all the things that you want to do. So I usually have this to-do list that grows longer and longer, and then I'm happy if in the evening I can tick off a few things, but I never finish. So meanwhile I can sleep properly, but at the beginning I always had the feeling I'm not performing well enough because I don't manage to do all the things that I should do. But you get used to it. You get used to many things in life. But my main problem, my main struggle is, I think, really the lack of time. So it's impossible to do parallel processing. People know that. But sometimes I still try, and then I don't manage. So the best is still to do the most important thing, and then to do the next thing, and maybe not worry too much about the day after. At least I'm trying.
Yeah, you said you experienced a phenomenon for yourself once, the so-called imposter phenomenon. Maybe you can explain it better.
Actually, we talked about this briefly, before this interview. I found this just a very interesting psychological phenomenon about which I'd never heard before, and I recently read about it, so that's why it came up here in this situation. So this imposter phenomenon is an effect that often concerns people who are highly educated and to achieve very well. So people who have a doctoral degree or even are professors. And it means, this imposter phenomenon or imposter syndrome means that you think that you are an imposter. So you think that other people judge you higher than you actually deserve. So like if you're a doctor, that maybe you don't really deserve this doctoral degree, something like that. And it actually occurs with many young scientists, I read in this article. So that's why I also thought maybe it's an interesting topic to touch here, because maybe there are people around who feel the same and don't know that this phenomenon exists, and it's very common actually. And in my case, it was kind of a revelation because I also experienced this phenomenon. And actually, I still remember the day before my PhD exam, I had exactly this feeling. So tomorrow I will have this exam, but I'm not really ready. I mean, why should they give me this PhD degree? Yes, I've done a little bit of work and I've published some papers, but I don't feel that I deserve it. So I had this inner feeling. I didn't talk with anybody about it because you don't talk with people about this. And then I thought, well, tomorrow they will find out. But in the end, they didn't find out. They gave me the degree, I got a good mark and so on, and everything continued. But this feeling was there somehow. And that's why I found it so interesting to see after many, many years now, recently, that it's something known in psychology, and that actually quite a few people are concerned about that. And, well, I don't want to say suffer. So, of course, I didn't suffer. It was just an internal feeling, so I didn't change my career. So if somebody thinks about changing the career, then one should take a step and change it. And actually, at first I thought that it concerns mostly young women in science, but this doesn't seem to be true. So it seems that statistically both men and women experience this phenomenon. And then it gets better when you get older, because then at some point you don't worry so much about yourself anymore, because you take responsibility mainly for others. And this is also true for me, because now other people are the ones for whom I have to find problems to solve, and I have to care for them, and etc. So I don't care so much about myself anymore and about my worries.
But you have, so what I have seen, you have quite accomplished a lot of things. And maybe let's talk about the things you have accomplished. So you are quite, you do quite a lot in quantum key distribution. Mm-hmm. And maybe before coming to quantum key distribution, we should explain a few things about quantum computation and what the problems are. So you talked about Shor's algorithm and Grover's algorithm, and as far as I understood, this Shor's algorithm is about the reason that to be a problem that it could solve the cryptography of normal computers. And in this case, it could be quite, so to say, dangerous for cryptographic keys.
Yeah, that's true. In fact, so if the Shor algorithm would be performed on a quantum computer that still doesn't exist in its full glory, let's put it like that, then conventional cryptographic methods would be in danger. So you mentioned RSA, this public key cryptography that is used nowadays, and that relies on the fact that nowadays it's very difficult to factorize a large number, to find the prime factors. So this is a function that is asymmetric. So if I tell you a number, let's say I give you a number and you're supposed to find the prime factor. So I tell you the number 91. Can you tell me the prime factors of 91?
Of 91?
It's not so easy, no? So how would you do it to solve this problem? How would you start? You would start
I will check whether first divide by 2 to get the first prime number, exactly. And realizing that it's not possible in 91. And I think I would start then with 3, which is also not possible for 91.
Exactly.
And in the next case, I would go for 5, which is also impossible for 91.
Exactly.
So going by each prime number.
And then the next one would be...
Yeah, 7.
7.
And it should be divided by 7. It's 17, and then 70, and then it's 21, so it would be 13.
Exactly. So you found the prime factors of 91, it's 7 times 13. But it took you quite a while, no? And we saw also that the algorithm that you used was a good algorithm, but it's very long, no? Now imagine that you have a very, very long number, it will take ages. But the other way around to solve this problem, so if I give you the prime factors and you are supposed to find the product of the prime factors, this is easy, no? If I tell you multiply 7 times 13, it's easy. So you have a clear algorithm. You multiply 7 times 10, it's 70, plus 7 times 3, it's 21, 91. So this is an example of a function that is asymmetric in the sense that in one direction it's very easy to solve, multiplication of the prime factors, and in the other direction it's very difficult. And that's somehow the basic idea of public key cryptography, where for the encoding you use a key that is publicly known, 91, but then the private key is very difficult to find. And the private key is only known to the legitimate users. And yeah, but now, as you said, if Shor's algorithm comes up in the quantum computer, suddenly you can factorize very, very large numbers, and RSA would become completely insecure. And that's where quantum crypto sets in, or quantum key distribution, or QKD, as you correctly said, where the idea is that you use the properties of quantum mechanics in order to establish a key that is random and that is only known to the legitimate users. So in this sense, quantum computing is a danger for classical cryptography, but at the same time, quantum cryptography offers a solution to this problem. And that's why people were so excited when the first protocols on quantum cryptography, or nowadays people say more often quantum key distribution, when these protocols came up. And the first one was in the 80s already, in 1984, by Bennett and Brassard. And they described how to realize such a protocol by sending single polarized photons. And then actually the second protocol was done by Arthur Eckert, my boss in Oxford, who described how to do QKD, quantum key distribution, with entangled systems. And somehow this is the very first idea that is nowadays very famous in so-called device-independent QKD, where you don't need to make any assumptions about the devices. But Arthur at that time already had this idea that if you have entanglement, you can somehow prove that your system has quantum properties, and that an eavesdropper, now we come back to the no-cloning theory, because the eavesdropper would like to learn the state of the quantum system, So usually the eavesdropper is called Eve for obvious reasons, because the similarity of the words. So she would like to copy a state that is passing between the legitimate partners, but she cannot copy it perfectly, as we have seen in the no-cloning theorem. And that offers the security of quantum crypto, because a perfect state, an unknown state, cannot be copied perfectly.
And you are basically setting up protocols or defining protocols in order for quantum Q distributions. In one of your publications, you had Alice distributing, for instance, to many Bobs. And in between Eve, who should not be able to or better to say Eve, who should get as less information as possible. Maybe you can explain more to that.
Yeah, you described it already very well. So recently, actually a few years ago, we started here in Düsseldorf to think about a more general situation. So before I was describing the scenario where two legitimate partners want to communicate, and they're usually called Alice and Bob. And then at some point we thought, but what if more than two people want to communicate? Can we generalize this whole idea of quantum cryptography, quantum key distribution to more than two people? And then we came up with ideas how to do that. So looking at entangled states that might allow such a multipartite quantum key distribution between one Alice and several Bobs, as you said. Well, actually, many people call this scenario also conference key agreement, because you can run, for instance, an online conference between many people. We all know about these online conferences now. And then if everybody in the online conference shares the same key, then you can communicate in a secure way. So conference key agreement is maybe the terminus that people use mostly nowadays. Yeah, and then there is poor eavesdropper Eve again, and she wants to intercept the messages. She wants to eavesdrop. And again, you can bound her knowledge by calculating the information that she can gain by doing an attack on the system. And actually also in the context of ML4Q, we have a very nice project in this direction, where Glaucia and Federico from my group, they actually do exactly this. They are doing calculations in a protocol for so-called device-independent conference key agreement, where they don't make any assumptions about the devices, but they need to prove that the system is quantum by showing the violation of a certain inequality, a so-called Bell inequality, now for many people. And then, once you're given the violation of such an inequality, you can, or they calculated these bounds on the information that an eavesdropper can have, and also they can calculate also bounds on the correlation between all the parties. And these are highly abstract calculations, very theoretical, very elegant, very beautiful. So it's a very nice project in this context of ML4Q.
Yeah, I've already seen that's quite also very mathematical. Your papers are very mathematical with stated theorems and corollars, and quite different to more of the device side, like me, who studies material and just is more like it's really based on the crystal structure and really settled on the material itself.
Yeah, well, it may look different, but I think in the end we also want to connect to the experiment. So yes, right now this project is still very mathematical, but in the end we also want that the protocols are implemented in an experiment, and then you have to deal also with very explicit situations where you have noise models for the experiment, so you have to integrate that into your model. You have to look at the experiment. Maybe there are some side channels for attacks of Eve, so you have to try to understand also the experimental setting much better. But this will come at a later stage. So actually right now, in the project that I described, we don't yet have any implementation. But I also find it interesting and very necessary to still keep this link to the real world, to the experiment. And of course also within ML4Q there are very direct links to an experiment in Bonn, for instance. And yeah, this is part of the game. So I think both aspects belong together.
Yeah, it's always hard to imagine how something like this could be implemented in a quantum computer. I've just seen that there are possibilities to also implement logic structures, and I mean it's quite intuitive to do it with a bit system where you just have 1 or 2, and it's so hard to imagine that it can be possible for a quantum which can have basically everything.
Yeah, that's true. You're mentioning one of the central points actually of quantum information processing. So yeah, in classical information processing you have bits, no? You said 1 or 2, or usually we say 0 or 1, and suddenly in the quantum world you can also superimpose 2 basis states. So let's call the basis states still 0 and 1, but now you can make any possible linear combination of the 2, and so you have infinitely many states, and how do you deal with them? But the really ingenious thing is that, people who invented quantum gates also showed that you only need a very small set of so-called quantum gates to operate on these qubits, and that with a small set of gates you can reach any possible transformation. So basically you can calculate any function on a quantum computer by putting together small gates. So 1 qubit gates and 2 qubit gates. This is the so-called universality of quantum gates. So in the end, this problem of having infinitely many states and dealing with them in a very large Hilbert space can be reduced to a tractable problem, let's say. At least for theoreticians. For experimentalists, it's still a very difficult problem.
Yeah, so now I have 1 or 2 questions for you. And you have to answer them briefly and maybe very quick, so don't think too much about them.
Okay.
Here comes the first. Von Neumann or Shannon entropy?
Von Neumann, because it's quantum.
Bit or qubit?
Well, what can I say? Qubit.
Oxford or Torino?
Oh, that's more tough. In fact, now on Sunday we have the final of the European Soccer Championship, and it's England versus Italy. So, no, it's a superposition of Oxford and Torino. Because I like both countries, and I like somehow people in both countries.
That's okay. I've heard you singing in the choir. Soprano or con alto?
Alto, of course.
Alice and Bob or Eve?
Alice and Bob.
Turing or Feynman?
This is also difficult. So Feynman for me stands for physics, and Turing stands for computer science. I'm a physicist, so I have to say Feynman, even though my way of thinking has been influenced by Turing a lot.
So it's also a superposition.
It's also a superposition. We always come back to the quantum world.
Yeah, and then Shor or Grover?
Shor is more powerful. It gives an exponential speed up.
Yeah, then is there anything... So if there's one thing that is most impressive for you about quantum cryptography, what is this to you?
The thing that is most impressive about quantum cryptography, maybe it's the fact that it's the link between a deep and fundamental property of quantum mechanics, namely the fact that, well, I said you cannot clone an unknown quantum state perfectly. One could also say it's the uncertainty relation. These are just different faces of the same medal, I would say. So you have this very fundamental aspect of quantum mechanics, but now in this stage of the research in quantum information processing, people are thinking about really applying this for security measures in our communication society. So we live in a communication society, and of course we have a lot of encryption and decryption methods to make our communication secure. But this possibility that this might change our lives in the future, I'm not talking about this year or next year, but maybe in 10, 20 years, this might influence our daily lives. I find this very interesting, that there is this link from the elegant, mathematical, abstract physical description of quantum physics to our daily lives, which maybe we will see in the future, but we don't know yet.
Thank you very much, Dagmar, for giving this interview, and I'm pretty sure that it motivates quite a lot of physics students to head to this direction of physics and study that topic.
Thanks a lot, Kathrin, for these very kind words and for asking me really difficult and also very nice questions. It was really a pleasure to talk to you.
Thank you very much. It was a great pleasure to talk to you.
Thank you.